Hello and welcome to lecture 7 of ECE 3337. We're still talking about linear time invariant systems, and the reason why I decided to video record this lecture is because I asked you to work a bunch of problems in class, and I wanted to make sure that you had the solutions to that, and you sort of watched me solve these problems with you. Okay. Okay, so in the previous class we talked about the convolution integral. The convolution integral is a very empowering tool because it allows us to calculate the response of a linear time invariant system to virtually any reasonably well-behaved input. Okay, so if the input to the linear time invariant system is x of t, all I need to do is to know the h of t, which is simply the response to an impulse. So I just take the special input called the impulse, okay, and I apply that to the system, see what output it produces, and that's my h of t. And that is a complete characterization of the linear time invariant system, right? That's a very, very cool thing, right? That means the system behaves the same way over and over again, okay? Now, if you know the impulse response to the system, then the output is given by this, rather simple formula, which is x of tau, h of t minus tau, d tau, integrated over minus infinity to infinity. So you got the input signal, x of tau, and you got the impulse response. That's been flipped and translated. So this minus sign here tells you that this has been flipped. It's like time reversal, right? It's been time reversed, and then it's been shifted by t, okay? So this flipped and shifted version of the impulse response is being multiplied by x of tau, and then the product is being integrated, okay? Now, in most cases that are of interest to us, we'll find that the limits of these integrals are, not exactly minus infinity to infinity, but something much smaller, right? For example, if you're dealing with causal systems, we'll see that this guy, the lower limit, usually goes to 0. Okay, and it gets simpler than that. You'll see some of that in today's examples. So as another recap, we have looked at a bunch of properties of the convolution function. The first of these properties says that when we're dealing with causal systems, a system is causal when its impulse response is 0 to the left of the, 0 to the left of 0 on the time axis, right? So now and in that case, the lower limit just becomes a 0 for the convolution integral. Now, we looked at a bunch of properties for the convolution operation. The first one is commutative, right? It tells you that it doesn't matter in which order you do the convolution. So you can swap, okay, x and h. So now thought another way, you can think of a signal as a system and vice versa. It doesn't matter, right? It gives you the same answer. That's kind of interesting, right, in its own right. And we can put some of those properties to use a little bit later. You'll see some of that. Now the other property number 2, is associativity, right? So what that tells you is that if you were to have 3 functions, say g, h, and x, that you want to all convolve, together one after the other, one way to do it is to convolve g and h together, and then take that result and then convolve that with x, right? What this theorem tells you is that you could have also done it the other way, right? You could have done h and x first, okay, convolve them first, and then convolve that result with g. You'll get the same answer. Now, distributivity, okay, tells you that that convolution behaves kind of like a multiplication. In other words, it distributes over addition, right? Now, if you had a bunch of functions, h1, h2, h3, and so on, hn, right? And if you were to take their sum and convolve that with x of t, it's the same as convolving x of t with each of these terms, h1, h2, and so on, and then taking the sum of their convolutions. This is a surprisingly powerful idea, right? It's sort of telling us that you can take a signal, say h of t, and represent that as a sum of other signals, maybe simpler ones, and then convolve it with x of t, right? Now, if it's easier to do what you see on the right, in other words, it's easier to do these convolutions with the individual component signals, right, of h of t, h1, h2, and so on, then you can convolve them individually and then add up the responses, right? That's a cool idea. Now, property 4 tells us that if you convolve two causal systems, you get a causal response, right? The y of t will be causal. That means everything to the, where t is less than 0 is 0, okay? Now, this is also kind of interesting, the time shift property, right? And when you come to think about it, it has to do with the time invariance, right? So if you were to shift, say, the input by t2 and the impulse by, say, t1, then the overall output is simply delayed by the sum of these two delays, right? And then the other property says that if you convolve any signal with an impulse, you get a snapshot of that signal. And the snapshot happens when whatever is inside the delta, right, goes to 0. So when t minus t is when t equals to t, little t equals capital T, that's when this delta function has a non-zero value, right? That's the point at which this signal gets snapshotted. Okay, you gather a snapshot of that. Now, the other theorem has to do with the width, right? So, for example, if you have a signal, okay, with a finite width, what that means is that it's 0 over here, it's 0 over here, but over this region it has some non-zero value, right? So the width is the time period over which the signal has some non-zero value, right? So for these types of signals, right, the convolution operation simply adds up the widths, right? And it makes sense. So if this was like x of t, right, and if h of t lasted, say, okay, that long, then the last of x of t will still produce an output, okay, till to the point at which the impulse response width, okay, lasts. So basically the width of y, okay, equals the width of x plus the width of h. Okay, this is also a very simple and interesting property that comes in handy. In like fashion, okay, the integral of y of t, which means it's the area, right? Okay, is equal to the area under, okay, so this is the area, right? So the area under y, okay, is equal to the area under x plus, okay, sorry, times the area under h, okay. Now the other property we talked about is that the convolution of any signal with the unit step function simply makes that signal be integrated, okay, wherever the unit step response is a non-zero, right? So unit step goes like this. So it's a 1 to the right of the axis and 0 to the left of the axis. So the unit step doesn't amplify the signal or attenuate it in any way. It simply, multiplies it by 1 to the right of this. So if you multiply any signal, x of t, with u of t, right? And if you if you convolve any signal with u of t, right, you get x of tau, okay, u of t minus tau d tau, right, integrated like that. And this product, okay, is going to be is going to be equal to x of tau, right? And that's going to happen wherever the unit step function okay, is equal to 1, right? So that's what's going on here. Right? So another way to do this is to write this as u of tau x of t minus tau d tau, right? And you can sort of see that wherever tau is greater than 0, okay, this step is going to be 1, and you just get to integrate this guy over tau greater than 0, right? So now for the purpose of this class, we'll skip property 10b, okay? I'm not going to examine you on that. Okay, so let's go in. Now, how do these properties prove to be useful, right? That's the question. So now one way to see that is to revisit our example with the RC circuit, right? So you got the familiar, RC, okay? This is ground. This is V input, and this is V output. Okay, so for this circuit, we know that the impulse response, h of t, is given by 1 over RC e to the minus t over RC, right? Now, we call tau c equals to RC. This is what we call our time constant. Okay? Now, suppose that our time constant equals 1. Okay, so to keep things simple, let's try to figure out the response of the circuit to an input voltage that in the shape of a triangle, like that, right? So V input as a function of time kind of looks like this, right? The output goes up to 1, okay, and then falls down like that. So the question is the following. Knowing the impulse response is supposed to be, right, all that we need to know about this circuit, right? So with just this alone, can we find the response of the circuit to this input? That's the question, right? Now, how do we go about doing that? Now, one observation we can make is that this signal that we see here, okay, is composed of a bunch of ramps, okay? So you got ramp number 1 here, and you got ramp number 2 here, right? Sort of an up ramp and a sort of a down ramp, right? Now, we know some signals already, right? So if you were to take the unit step function, right, u of t, which kind of looks like this, right? Now, if you were to integrate that, you get the ramp function, which goes like that. We call that r of t, right? So r of t equals t, right? Because it grows with time like that. Because the longer you integrate the unit step function, the higher the ramp goes. And the area under the unit step function grows linearly as you keep integrating in this direction. Okay, so this is a linearly growing function. So knowing that, can we figure out, okay, how to find the response of this circuit? And why am I thinking about the ramp? I'm thinking about the ramp because we can easily calculate the response to a ramp. Now, if I can express this signal as a function of a bunch of ramps, okay, then we can try to reuse that, okay, the ramp response over and over again. So let's see how that works, right? So suppose I have the ramp function. This is time t, okay? So the ramp function goes like that. Now if I were to delay this by 1, okay, I can get another function that's a ramp of t minus 1, which is equal to t minus 1. Now if I delay that by 2, I get another ramp function, which is r of t minus 2, okay, which is given by t minus 2. Okay. Now let's think a little bit about what happens when you subtract these ramps, from each other. So suppose I were to do r of t minus r of t minus 1, right? Let's see what happens. So This is time t. Okay, I'm going to subtract this guy from this guy. So all the way up to time t equals 1, okay, the second guy is 0, so the difference keeps increasing all the way up to 1. But then after that, the difference between these two signals stays essentially constant, okay? And it no longer increases, right? So basically you get that, okay? Because the the signal starts out at this point, okay, at 1, and every increase in this is matched by an increase in this. And those increases are exactly the same. They cancel each other, and you get a flat signal. Now, what if I were to try the following, right? R of t minus 2 times r of t minus 1, right? So in that case, it keeps increasing, okay, up to 1 as before. But then after this point, 1, right, what happens is that, in addition to this flat area, which, okay, in this curve, I can start to subtract a ramp out of this, right? So I can get that, okay? So now what if I were to take another ramp, okay, that starts off here? I can exactly cancel these two guys out, right? So suppose I do the following. T, okay, r of t minus 2 times r of t minus 1, okay? And then I counter this with another ramp here, okay? So r of t minus 2, right? Then what I have is a signal that goes like this, okay? Increases all the way up to 1, and then, okay, it decreases up to 2, and then it says 0 after that. It says 0 after that. This is our input signal. So our input signal, okay, can be modeled as r of t minus 2 times r of t minus 1 plus r of t minus 2. Okay? So this is pretty cool. So what I've done is that I've taken a complicated looking signal and I've represented them as a sum and difference of simpler signals, right? So if I know the impulse response to r of t, okay, the response to a ramp, r of t, then I can figure out the response to a delayed ramp, r of t minus 1, and the other delayed ramp, r of t minus 2, and basically do, a linear combination of them in order to figure out the output to this. Okay, so our next task, okay, is to figure out, the ramp response. Okay, so the ramp response, suppose I were to denote that by z of t, okay, is given by h of t convolved with the ramp r of t. All right, so let's figure out what z of t is. So we know what h of t is, okay, is e to the minus t ut, okay, because our tau c is rc, is just 1, okay, for that reason. So our convolution integral, z of t, okay, is given by the integral of the impulse response, h of tau, right, which is e to the minus tau, okay, u of tau, with the ramp response, right, with the ramp signal, which is r of t minus tau d tau, right? So we're going to integrate from and of course, you know, there is a u of t minus tau there. Okay. So if you look at this signal here, this is a 1 whenever tau is greater than 0. Okay. If you look at this guy here, it is a 1 when t is greater than tau. Right? Now, for both these unit step functions to be a 1, okay, we can sort of see that it happens when tau is greater than 0, same thing as this, and tau is less than t. That means that this integration, okay, can go from 0 to t. Okay, so cleanly rewritten, okay, this is what it looks like. 0 to t, e to the minus tau, okay, and now our ramp function is simply equal to t minus tau, right? T minus tau d tau. Okay, so this is equal to, okay, integral from 0 to t e to the minus tau times t minus integral from 0 to t d tau, okay, tau e to the minus tau, okay, this thing d tau. Okay, so this t can come outside. So this is t times integral from 0 to t e to the minus tau d tau, okay, minus integral from 0 to t tau e to the minus tau d tau. Okay, so I'll let you work through these two integrals. Now this is the product of two functions. Okay, you can choose to either um, you know, do the integration by parts, or okay, if you're in a hurry, you can actually look up the table of integrals that's in the back of the textbook. Okay, and if you look at this guy on the second to last entry here, okay, that describes this integral. Okay, you can either use that or the other and sort of figure out the answer, and it turns out to be, okay, e to the minus t plus t minus 1, okay, times u of t. So once you have the z of t like this, you can stick it into the other formula. Remember, our v input of t is, you know, r of t minus 2 r of t minus 1 plus r of t minus 2, correct? So my v output of t, okay, is going to be h of t convolved with, okay, v input of t. Now this guy can be expanded into this, okay, which means I have to convolve h of t, okay, with r of t minus 2r of t minus 1 plus r of t minus 2, okay? That should be better. So v out of t is h of t convolved with r of t, which is simply z of t, minus 2 times h of t convolved with r of t minus 1, which is z of t minus 1, okay? Oh, here it is, okay. Z of t minus 1 plus h of t convolved with r of t minus 2, which is z of t minus 2. So now I know what z of t is, okay? We just stick this into that and we get the final answer. Okay, and if you work through that, okay, you get the complicated looking signal that you see on your left, okay, and if you plot it out, okay, you get the same response as we did last time, except we got to that answer much more easily this time, right? Because we took advantage of the impulse response of the system, right? We also took advantage of some of the properties of the convolution integral, okay? So this is where it comes in handy. So imagine you have a table of properties of the convolution integral, and you had another table which is, a standard set of convolutions, right? That you can potentially even memorize or, put on a crib sheet, right? Then you can put two and two together to perform complicated convolutions much more easily. Okay. Now again, sort of the grand, ECE idea that's at play here is the following, right? You got a complicated signal, okay? You break it up into little parts, okay, which are easy to deal with, okay? Now you process each of these easy parts, okay? And then you add up the results together, okay? And that gives you the final answer. Okay, so this is another way to go about this. And this type of divide and conquer idea, okay, occurs frequently in engineering. Okay, so it's not just an ECE idea; it's an engineering idea. Okay, and we use that a lot. Okay, our next job is to do a little bit of convolution practice. Okay, and one of the things I wanted you to do is to basically work through the uh, table 2-2 in your textbook. Okay, so table 2-2 in your textbook has a bunch of properties, and we would just want to work through them so that you have an understanding of convolution and sort of the mechanics of how to do the convolution. Now these examples on the scale of things are going to be relatively easy, but until you master these, you'll have trouble with what follows. So what I thought I'll do is I'll work through them for you, okay, and then we'll sort of build up from there. Okay, so let's look at problem number one, right? So you got a step function u of t, which is being convolved with u of t. Okay, and we want to find out what that is. In fact, we want to show that this is simply t times u of t, right? So how does this process work? So this is kind of like my x, this is kind of like my h, okay? And I'm going to stick them into the convolution formula. So I get minus infinity to infinity, okay? So this is like my y of t. Y of t is convolution from minus infinity to infinity, x of tau, which is u of tau, okay, times h of t minus tau, right, which is u of t minus tau, okay, d tau. All right, so where were we? So now this guy is going to be 0 except when tau is greater than 0, okay? And this guy is going to be 0 except where t is greater than tau, right? So the part of the axis where both these guys are non-zero, okay, is tau greater than 0 and tau is less than t, right? So what that means is that this integral is simply integrated from, goes from 0 to t, and it's 1, okay, times d tau, okay? So this is simply tau, okay, comes from 0 to t. This is simply equal to t, okay? Now this whole thing is causal, right? So I'm going to write the output as y of t is t times u of t, okay? And this is our answer. Now let's go on to question number 2, okay? Let's see how that works out. Question number 2, we're asked to convolve e to the at ut, okay, with u of t. So we again start by writing down the convolution integral, right? So y of t equals integral from minus infinity to infinity, okay, e to the a tau u tau times, okay, u of t minus tau d tau, right? Now we go through the same logic here as we did for the previous question, and we come to the same conclusion that this product is a 1 when tau lives between 0 and t, right? So we get 0 to t e to the a tau d tau. Now the integral of e to the a tau is simply 1 over a e to the a tau, right? And this is going to go from 0 to tau. So the answer is 1 over a, okay? And so e to the at, this should be t, okay? E to the at minus e to the a times 0, which is 1, right? So this is our answer. And then, of course, we put a u of t at the end because the whole thing is causal. Okay, so this is our answer. Now, let's try problem number 3. Right, in problem number 3, we are asked to convolve e to the at, okay, again, a causal thing, so we multiply by u of t, and we want to convolve that with, what do we have here, e to the bt ut, right? So, again, the ritual is still the same. We write down a convolution integral from minus infinity to infinity, okay? This is kind of like our x, so we write x of tau, right? So e to the a tau, u tau, and times, okay? This is, we need to write, this is our h of t, okay? We need to write h of t minus tau, which is e to the b t minus tau, u of t minus tau, d tau, okay? And by the same logic that we went through here, right, this product is going to be 1 when tau is between 0 and t, right? So this whole integral becomes from 0 to t, okay, e to the a tau, okay, e to the bt, and e to the minus b tau, d tau, right? Now this guy can come out of the integral because we are integrating with respect to tau, not t, okay? So it's a constant. So we can get e to the bt, integral from 0 to t, okay, e to the, okay, a tau minus b tau is simply a minus b tau, d tau, okay? So this is given by e to the bt, okay, integral from 0 to t, so e to the a minus b tau, okay, so 0 to t divided by a minus b, okay? So let me rewrite that here on the sheet. So y of t is e to the bt, okay, e to the a minus b tau divided by a minus b, okay, going from 0 to t, okay. So this is e to the bt, okay, divided by a minus b, you can take it outside, okay, times e to the a minus b t, okay, minus e to the a minus b times 0, which is just 1, okay. So if I expand this out, I get 1 over a minus b. I can multiply this with each of these two terms, and I get e to the a t minus e to the b t, okay. And then, of course, I multiply the whole thing by u of t because it's causal, okay, and this is my final answer. Okay? I hope you're getting the hang of this stuff. Okay, so our next problem is problem number 4. Now, problem number 4 is sort of a special case, okay, of problem number 3. Okay, when a is, tends to b, right? It's in the limit. It's kind of, if you were to take the limit as a tends to b of, problem 4, okay, the limiting case should be like problem 3. That's one way to think about that. But the trouble is that you have a minus b in the denominator, and you can't just set a equals to b because that's meaningless, right? Because denominators can't be 0. So one way to do that is to take this formula and take the limit of that as a tends to b, or we can work from scratch, right? So we are asked to convolve e to the at ut with itself, right? So I write down the formula from scratch. I write minus infinity to infinity. This is a y of t, okay, is e to the a tau u tau times e to the a t minus tau, okay, u t minus tau d tau. Now the same thing happens here, okay, so these two guys, you know, will only be one at the same time when we are between 0 and t. So e to the a tau times e to the a t times e to the minus a tau d tau, right? Now these two guys cancel, right? So the integral reduces to integral from 0 to t e to the a t, okay, d tau. Now e to the at can just jump outside, right? Because we're not integrating with respect to this. So this becomes integral from 0 to t, okay? E to the at comes outside. Let me write it more cleanly. E to the at integral from 0 to t d tau. And this integral of this is just t, right? So the answer is t times e to the at. And of course we stick a u of t at the end because it's all causal, okay? So our answer is y of t equals t times e to the at ut. Okay? All right, so let's go on to the next problem. Okay, problem number 5. Problem number 5 wants us to integrate t times e to the at ut, okay, convolve it with e to the bt ut, okay. It's just a little bit messier than the previous question because we got this guy here, okay. This little guy has been added to the whole thing, okay. And of course we are given that a is not equal to b because our final answer is going to have one a minus b in the denominator, right? So we are already given this, so our denominator will not go to 0, so we can move forward. Okay, so let's write down the convolution integral. Integral from minus infinity to infinity, okay, tau e to the a tau u tau times e to the b t minus tau, okay, u of t minus tau d tau. Okay, we now know the usual routine with these two guys, so this becomes 0 to t tau e to the a tau e to the b t minus tau d tau. Now e to the bt can be pulled outside, okay, because we're not integrating with respect to t, so we get this e to the a tau, and then we get e to the minus b tau, so e to the a minus b tau d tau. Okay, now we need to sort of work on this integral, right? So one way to do that is to do integration by parts, right? Another way is to look at the table of integrals. So if you look on your left, okay, the next to last entry at the bottom, okay, is the case that represents this, right? So suppose I were to set a equals a minus b, then this integral looks like, you know, integral from 0 to tau tau e to the a tau d tau, okay? And this is given by, you know, a t minus 1 over a squared, okay, e to the a t, right? Sorry, it's a tau. Right? And then I have to sort of apply the limits from 0 to t. Okay, so y of t is given by e to the bt, okay, times this expression for t, which is a minus b, which is a, times t minus 1, okay, divided by a minus b squared minus this whole thing for the case when, okay, instead of for tau, okay, you stick 0 there, okay. So you get, on the numerator, you get minus 1 divided by a minus b squared. This minus and this minus cancel, so I'll just throw this out, okay, I'll put it down like that. And then e to the a tau is e to the a0, which is just 1. Okay, so this is e to the b. So this is e to the bt divided by a minus b squared, okay, times, what am I missing here? Oh, this should be e to the a minus b t here, okay. So I get a minus b t minus 1, okay, times e to the a minus b t, okay, then plus 1. So if we were to simplify that, okay, by multiplying everything out by this, okay, so when we distribute this over this, we get 1 over, you know, a minus b squared, okay, times a minus b t, okay, e to the at plus, okay, e to the bt minus e to the at, okay, so this is our answer. And of course, I need to multiply the whole thing by u of t, which I can put out here. So this is the final answer. All right. So let's move on to the next question. Question number 6. Now, question number 6 is the special case when a equals b, right? So when a equals b, right, we obviously can't, you know, just stick a equals b here because the denominator will blow up on us. So it, you know, one choice is to simply work from scratch, right? So let's just do that, right? So question number 6 says convolve t equal to the t times e to the at ut, okay, convolved with e to the at ut. Okay, so let's write down the convolution integral as usual. Integral from minus infinity to infinity, okay, tau e to the a tau u tau, that's this guy, x of tau. Then we write h of t minus tau, which is e to the a t minus tau u of t minus tau d tau. So we go through the usual routine with these two guys, and we know the limits of our integral are just going to be that. We got tau e to the a tau, and then here, okay, I can write this as e to the at times e to the minus a tau, okay, d tau. This guy cancels this guy, okay, and this guy can actually come outside the integral, right? So this is e to the at, let me write it more neatly, e to the at, integral from 0 to t, tau, okay, d tau. Now the integral of tau, d tau, is just half tau squared, right? So e to the at times half tau squared, okay, evaluated from 0 to t. This is e to the at times, I'll take the half outside, okay, so I'll put it here, which is t squared minus 0 squared, so it's just t squared. So the answer is, you know, y of t, in this case, is given by half t squared times e to the at ut. Okay, that's our answer in this case. I hope you got that. It's fairly straightforward. Okay, and this is our usual, standard kind of a ritual that we go through every single time. But the key to all these questions is to write down the convolution integral. Follow the definition, simply write it out. Okay, write it out accurately and methodically work your way through that, right? Okay, so our next question is which one here now? Question number 7, right? So question number 7 asks us to see what happens when we convolve a delta function with another delta function, right? So let's just think this through, right? So y of t, so this is kind of like my x, this is kind of like my h, okay? I'm going to write down the formula for y of t, right? Which is integral from minus infinity to infinity, okay? Delta of, x of tau, right? So it's tau minus t1 times, okay, h of t minus tau, right? So delta of t minus tau minus t2 and d tau, right? Now, let's think about what happens here, right? When I'm convolving two delta functions. Now, a delta function is 0 everywhere, okay? So suppose I write delta of t, right? And this is t. This guy is 0 everywhere except at the place where this argument t goes to 0, right? At that point, it tends towards infinity. But there's a bit of a caveat there, right? The integral of this whole thing, okay, going from t minus 0 to t plus 0 will always be a 1, okay, because of the way we constructed it. We started out with a rectangle of fixed area, and then we kept squeezing it in this direction so that it just had to grow in this direction infinitely in order to keep the area equal to 1, right? So for this to work, okay, we need to be able to, these two guys, these two deltas are going to only intersect when tau equals t1 and, okay, t minus tau minus t2 equal to 0, right? Which means if I were to stick this over here, I get t minus t1 minus t2 equal to 0. That's the only place where they're going to actually, these two delta functions will meet, okay? So you get a non-zero thing. Now each delta function has, integrates to unity, okay? That means 1. So multiplying the two delta functions will not change the integral. It'll still turn out to be a 1. But that'll happen at this point. Okay, so the answer to this question is delta of t minus t1 minus t2. Okay, so you get, if you convolve, so it's basically like one of these deltas is taking a snapshot of the other delta, right? It's taking a snapshot of it, wherever this guy goes to 0, right? So that's sort of what's going on here. So this is our answer. Okay, so for the next class, I'd like you to work through the textbook examples in sections 2.3 to 2.5. Okay, and the exercises that we did together today are going to turn out to be important because we'll sort of get the hang of how to do problems like this, and we'll have to keep doing more and more of these sorts of things, right? So it's important that you practice what we did today. Try to become quick at it, right? That's going to be important for you, right? And thank you, and have a wonderful, rest of the